In this presentation, I am going to explain Scott connection of transformers. By connecting two single-phase transformers in this method, Scott connection method, we can convert a three-phase input into a two-phase output. Now let us see what is meant by Scott connection. Actually, that was proposed by the scientist Charles F. Scott. And in this connection, Scott connection, this is a method of connecting two single-phase transformers to convert three-phase power into two-phase power or vice versa. So we can convert a three-phase power into the two-phase power or a two-phase power into three-phase power. What we are going to explain is the method to how can we convert a three-phase power into a two-phase power. Therefore, there are two transformers as such, and we'll be seeing later. One we call it as the main transformer, and the second one we call it as teaser transformer. Therefore, the main transformer and teaser transformer. And in this case, the key purpose of the Scott connection, that is first is the phase conversion. That is, the Scott connection allows for the conversion of a three-phase electrical power into two-phase system. This is beneficial for the system that requires two-phase power, such as specific types of motors that requires two-phase power and arc furnaces and some traction system. There, wherever we require a two-phase power, then from the three-phase power it can be converted by using this Scott connection. Another is that has got an efficiency improvement, that is improved efficiency by allowing the use of two-phase systems which can be more efficient for a certain application. The Scott connection can help improve the overall efficiency of the power system. For that purpose, we'll be using the Scott connection. As I already told, a Scott connection, there are two single-phase transformers and they are connected in this fashion. And this transformer, we call it as a main transformer primary, and this is called the main transformer secondary. Totally, we call it as main transformer. And this is the teaser transformer, that is the primary of the teaser transformer, and this is the secondary of the teaser transformer. Totally we call it as teaser transformer. Therefore, the two transformers, one we call it as main transformer and second one is called the teaser transformer. They are connected in this fashion so that the teaser transformer has got a, that is connected to one end of the teaser transformer is connected the middle of the main transformer. And regarding the number of turns, if N1 is the number of turns of the main transformer, this is the N1 by 2 and N1 by 2, total number of turns equal to N. At the middle point, that is the teaser transformer is connected, and the number of turns of the teaser primary winding is 0.866 of this turns, or 0.866 N1 is the primary transformer, teaser transformer turns. And of course, the secondary turns are both are equal. The secondary transformer teaser is N2. Similarly, that secondary transformer of the main transformer is equal to N2. And we'll be seeing the analysis in the coming slides. One of the transformer has a center tap, and that is the main transformer, and to that one the teaser transformer is being connected, and the number of turns here is equal to 86.6% of the number of turns of the main transformer. Now coming to the application of the Scott connection, that is first, as we have seen, it is a powering two-phase source. So the Scott connections are used to supply existing or specified two-phase equipments from a three-phase power grid. Therefore, it can convert a three-phase system into a two-phase system so that it can use to work two-phase motors, certain control motors where required two phases that can be used. Therefore, powering two-phase loads, that is a one application. Second application of the Scott connection is that electric furnace, that is the arc furnace, that is the connection allows for the balanced operation of the two single-phase furnaces from a three-phase supply. That arc furnaces can be operated by using Scott connection method of generating two-phase. For the railway electrification is the third one. A common application for powering single-phase traction motors on electrified railway line from a three-phase system. That is, from a three-phase system, it can generate a single-phase, two single-phase supply by using the Scott connection that can be used for the railway traction purpose. Another one is the linking power system. Therefore, it can be used to transfer the power between a three-phase and a two-phase system in either direction. It can transfer the power from a 3-phase into 2-phase or a 2-phase to the 3-phase. Therefore, the linking the power system is the another application of Scott connection. Now let us see the Scott connection. How can connect two transformers to form the Scott connection? Therefore, as I already told, there are two transformers. One we call it as main transformer, and the second transformer is called the teaser transformer. And this is the main transformer primary, and total number of turns of the primary is N1, or here N1 by 2 and here N1 by 2. This is the center point of the main transformer, to which the primary of the teaser transformer is connected. And this end is, or the number of turns of this one is equal to 0.866 times the number of turns of the primary. Then only we will be getting a balanced 3-phase power at the input side. Therefore, we will have to select 0.866 N1 at the teaser primary, and the secondary of this is called the main transformer secondary, which has got a N2 turns, and similarly the secondary of the teaser transformer is also having N2 turns. Therefore, the number of turns on the secondary of the teaser as well as main transformers are equal N2, and but the primary turns on the main transformer equal to N1, or the primary number of turns of the teaser transformer equal to 0.866 N1. This is the teaser, Scott connection of two single phase transformer, and the 3-phase input is given here. RYB is the 3-phase input is given, and the 2 phases are available. Here it is marked as V. This is equal to, this is marked as V1 and V2 here. That is here V2, and this is the voltage V1. The voltage across the teaser is marked as V1, and the voltage across the secondary of the main transformer is marked as V2. Therefore, these are the 2-phase voltage at the output, and this is the 3-phase input voltage to the teaser transformer. Or this is the, if you say phasor diagram, these are the 3-phase line voltages, like it is marked as VYB, VRY, and it is equal to VPR. For 3-phase balance, the voltage at the input side is coming here, and the output side, that is the voltage across the the teaser side, that is equal to V1, and the voltage across the main transformer secondary equal to V2. This is the 2-phase voltage available at these two secondaries of these transformers, and they are 90-degree phase shifted, or V1, or the voltage across the teaser transformer secondary is leading the voltage across the main transformer secondary by 90-degree. Therefore, this is a 3-phase input at this side at the input of the teaser transformer, and 2-phase is available here, which are shifted by 90-degree at the output of main transformer as well as teaser transformer. Or here teaser transformer voltage is, secondary voltage is leading the main transformer secondary voltage by 90-degree, and the both magnitudes are same. V1 magnitude as well as V2 magnitude both are same, but they are 90-degree shifted. Therefore, this is the waveform of the output of this transformers, main transformer and teaser transformer. It's a 2-phase output, and this is the 3-phase input at the input of this transformer of the the Scott connected connection of this input transformer voltage, 3-phase input voltage. Or 3-phase to 2-phase conversion is done by this method of connection, Scott connection. As I already told that how can we connect a two transformers into a Scott connection. We have a two single phase transformers. How can you connect these two single phase transformers to form the Scott connection? That we are explaining in this slide. Here, same as we have already seen this one. For the main transformer has a center tap primary at C. At this point, this is the main transformer primary. At the middle of that one, there's a center tap point which is notated as C here. For this is equal to N1 by 2. This is also equal to N1 by 2. The total number of turns on the main transformer primary equal to N1. The main transformer N1 has the primary turns, and the main transformer primary is connected between the phases Y and B. Between the phase Y and B, the main transformer primary is connected, and the teaser transformer is connected between the phase R and the middle point C. Therefore, here the teaser transformer is connected between R and C. Therefore, this is the teaser transformer primary, and this is the main transformer primary. And the teaser transformer primary is connected between R and the R phase and C, and the teaser primary has, this is the most important point, 0.866 N1, or if say for example, if this is equal to 100 turns, This is equal to 86. Of course, 100 means it is the 86.6 percentage of the this whatever the turns of this one. Therefore, that is the number of turns of the teaser transformer primary is equal to 0.866 times the number of turns of the main transformer primary. For 3 teaser transformer has 0.866 N1 turns, and the secondary of the main transformer has N2 turns. Therefore, secondary of this one has got N2 turns, same as the secondary of the number of turns of secondary of the of course, teaser transformer. Therefore, N2 both has got the same secondary turns N2 and N2, and here N1, but here the turns equal to, it is equal to 0.866 times the N1. Therefore, teaser transformer, one end is connected the middle of the main transformer, and this is a three-phase input voltage, and here we are getting two-phase voltages, or the magnitude of V1 equal to V2, but they are 90-degree shifted. Therefore, here as we have already seen that one three-phase signal, that is the input of the transformers, connected transformer is given, and the output will be getting two phases which are 90-degree apart. That is two-phase output voltage is getting. Of course, the voltage of the teaser secondary is leading the voltage of the main secondary by 90-degree, or you can say that one V1 is leading V2 by 90-degree. Therefore, this is the output at the teaser transformer, and this is the phasor diagram of the input of the teaser transformer, that is converting a three-phase input into a two-phase output. Therefore, here the input voltage, line voltages VRY equal to VYB equal to VBR, which is equal to the line voltage. This is the line voltage VL, magnitude all are equal. That is called a balanced three-phase input voltage is applied here, because magnitude of the line voltages are equal and they are 120-degree apart. And the output side here, the V1 and V2, that magnitudes are equal. Magnitude of V1 equal to magnitude of V2, and they are balanced two-phase voltages. Of course, the phase angle between this V1 and V2 equal to 90-degree, or V1 is leading V2 by 90-degree. In this slide, we'll be proving that if we are applying a balanced three-phase input here, we will be getting a balanced output voltage, two-phase voltage, in which you can see that we'll be proving that the magnitude of V1 is same as the magnitude of V2, provided we are applying a balanced input voltage, or VRY equal to VBB, VRY equal to VYB equal to VBR. If magnitudes are equal, then these two voltages V1 and V2 have equal magnitude. Of course, they are shifted by 90-degree. Now, transformation ratio, coming to the transformation ratio of the main transformer here, the transformation ratio means that it is equal to output voltage divided by, if you take the output voltage, V2 divided by input voltage is equal to the line voltage. Therefore, V2 divided by, we can get V2 divided by VYB, that is the voltage ratio of the main transformer. That is equal to the number of turns of this side, that is the secondary, that is N2 divided by N1, N2 divided by N1, or that implies that V2 divided by Vy, we can say that one VYB equal to the line voltage. Therefore, V2 divided by the line voltage equal to N2 by N1, or this voltage, the output of the main transformer secondary, V2 is equal to, from this equation we can see that it is equal to N2 by N1 into the whatever the line voltage. Therefore, this is the voltage available at the secondary of the main transformer, that is this voltage, V2 is that one magnitude. And of course, the transformation ratio of the teaser transformer, if you take that one, corresponding voltage here, that is voltage, we name it as V1. V1 divided by this voltage. What is this voltage? Let us see that one. That is the voltage between R and C. VRC. VRC equal to whatever the turns on this side, that is equal to N2 divided by, here equal to 0.866 N1. 0.866 N1. Now let us see what is this voltage VRC. Now coming to the VRC voltage here, if you see the phasor diagram here, this is equal, this is a VRC, that is the voltage between the phase R and this middle point. If you see the phasor diagram, this middle one, this is the VRC. And now to get VRC, that is equal to, if you take say triangle like this one, applying the Pythagoras theorem, here this one equal to this voltage root of VL square minus half of this one, or it is equal to root of VL square minus, of course this is equal to line voltage, half of line voltage VL by 2 whole square. or you can get it as VL into root of 1 minus, of course, equal to 0.25 or equal to 0.866 VL. For this voltage, that is, this voltage is equal to 0.866 VL, meaning that the voltage VRC equal to 0.866 line voltage VL. For substituting in this equation, we can get it as it is equal to substituting 2 in 1 V1 divided by VRC 0.866 VL equal to N2 divided by the number of turns here is equal to 0.866 N1, or we will be getting the voltage V1, that's voltage V1 output of the teaser secondary, that voltage magnitude equal to it is equal to which is equal to N2 by N1 into the line voltage. Therefore, you can see that this V1 and V2 are both are equal. From this, it's very clear that magnitude of V1, that is this one, N2 by N1 into VL, same as the magnitude of V2, teaser transformer secondary, which is equal to N2 by N1 into VL. Therefore, the magnitudes are equal. Two-phase voltage magnitudes are equal. And then next we'll be proving the angle between them equal to 90 degree in the coming slide. Therefore, this is a two-phase output available, that is across the main winding, that voltage is equal to V2, and across the teaser secondary it is equal to V1, and both have the equal magnitude, which is equal to N2 by N1 into the line voltage into VL. In the previous slide, we have seen that magnitude of V1 and magnitude of V2 both are equal. That is, this voltage magnitude and this voltage also equal, provided we are giving a balanced three-phase input at this point. That we have already proved it. Now we have to prove it that they are displaced by 90 degree. This voltage V1 is leading the voltage V2 by 90 degree. Now let us see that one. In a transformer, you can say that the phase of the voltage V2, that is this phase of the voltage, is same as the voltage phase of VYB. The same phase, because the phase of this voltage is same as the phase voltage of VYB, or main transformer primary voltage, that both phases are this is in phase to this voltage. Now let us see that similarly the voltage phase of this voltage is same as the phase of this voltage, the phase of VRC, same as the phase of VRC, or teaser transformer primary voltage. For this phase, the voltage at the teaser transformer has got the phase same as this VRC phase, and this voltage phase is same as the voltage VYB. Now let us see that one. In this case, for triangle, we can see that the VRC is 90 degree with respect to the VYB. Now VRC is that is the voltage at this point is, or across this one, is 90 degree shifted with this voltage, line voltage across that one. Meaning that here since this voltage is 90 degree with this one, meaning that this voltage is leading the main transformer secondary voltage by 90 degree. Therefore, thus the vector V1 leads the vector V2 by 90 degree. Of course, the magnitudes are same, but the magnitudes are both same, but the V1 is shifted by V2 by 90 degree, or V1 is leading the voltage V2 by 90 degree, or thus we will be getting a balanced two-phase output from a balanced three-phase input. Thus, the teaser transformer output voltage leads the main transformer output voltage by 90 degree. Thus, we are getting a balanced two-phase voltage from a balanced three-phase input voltage of a Scott-connected transformers. In this slide, I will be explaining for a balanced two-phase load. That is, we are connecting a balanced two-phase load, means load currents are equal into main as well as teaser transformers secondary. And for a balanced load current at the output, the input side current is balanced. The current through these phases, three-phase inputs are balanced, and meaning that they all having the equal magnitude of the current magnitude, as well as they are shifted by 120 degree. Now, current through the main winding, the current through the main primary winding, that is this secondary is loaded with the loads are equal at the both teaser and main transformers, and the current through this main primary winding due to the secondary main load here, as per the principle of transformer, the current in this main winding can be calculated as N, that is whatever this turns of this one, N2 by N1 into the current through this one, that is I2M, or N21 N1 I am notating as K, the constant K. Therefore, K into I2M is the current through the winding due to the load current at the main winding. Similarly, the current through the teaser transformer primary due to the load current, which is equal to I2T at this side. Therefore, that is equal to, again here is as per the transformer principle, it is equal to N2 divided by, number of turns here is equal to root 3 by 2 N1. Therefore, N2 divided by root 3 by 2 N1 into whatever this current, secondary current as such, which is equal to I2T, or which is equal to 1.15 K, where K equal to N2 by N1 times I2T. Or here I2T is the current through this one, and that is equal to 1.15, this constant N2 by N1 times I2T is the current through the primary winding of the teaser. So this is the primary current. Now that's because one observation is that this current is same as this line current. In this one, it is noted as phase A. Phase A current is same as this primary current, which is equal to 1.15 K times I2T. Now here just we can consider the load. First, I am considering the load power factor equal to unity. Load power factor is equal to unity means that the corresponding this voltage and this current, this current, they are in phase. Similarly, this voltage and this current are in phase. Therefore, this is the output voltage and current for a unity power factor load. And due to this current that is reflected on the primary side, that is we have explained this one, K into I2M, that is on the primary side of the main wind. And here 1.5 K into I2T, that is the primary side of this teaser transformer. And this is, therefore, that is actually, therefore here the total line current, to calculate the total line current of the main winding, it is here the teaser current, that is which is equal to 1.15 K into I2T, that is splitted into two equal in this winding equally, or that is it can be written as 1.15 divided by 2, or 0.58 K I2T is flowing through these two windings. And that for the total current through the line current, if you calculate the total current through the line, which is the vectorial sum of the current, this one K into I2M, that is which is written as here K into I2M, that is to that one half of this current is added, 0.58, that is 0.58 K I2T is added here. For this is the total current at the at the primary side of the main winding. Therefore, this is the method of adding that one. Or if you add that one, we'll see that one. This is a, of course, the line current of these three phases will be proving that all phase currents are 120 degree apart and have equal magnitude if you are giving a balanced load at the output side. Therefore, the line current through the phase A equal to the line current through the phase A same as the current through the teaser winding, primary winding, which is equal to 1.15 times K into that whatever this current I2T. Therefore, the current through the primary winding, that is the current through the primary winding, that is half due to the primary winding of the main transformer. That is current through the primary main winding, half due to the primary teaser current due to the dividing. It is a half only going through the teaser current, which is equal to 1.15 times K into I2M divided by 2, which is equal to 0.58 K times I2. Therefore, because of the teaser current that is split into two components, and due to that one 0.58 K I2T is coming here. That is this component. For this component is because of the load current at the main secondary, that is this vector, and this is because of this half of the teaser current, and the total current is through the line is given the vectorial sum of these two things. Therefore, if two phases are that is equal to, if two phases are balanced, we can say that I2T equal to I2M. I am taking it is equal to I2. I am replacing I2T and I2M equal to I2. For the line current through the phase B and C, line current through the phases B and C, it is the vectorial sum of Ki2, that is Ki2 means this current due to this current what is induced, or that is due to that one the current through the winding, that is added vectorially to the half of the teaser current, and 0.58 Ki2. We are adding vectorially, they are 190 degree apart, so that the total current equal to root of Ki2 whole square plus 0.58 Ki2 whole square, or that becomes 1.15 Ki2. Or this vector, we can say that one, this vector equal to same as this magnitude, which is equal to, already we know 1.15 Ki2. The current through this phase equal to 1.15 Ki2. Therefore, the current through this phase B and C same as this current, which is equal to 1.15 Ki2. That proves that all the currents are equal. 1.15 K into I2, where K is equal to N2 by N1. I2 is a balanced secondary current, and these line currents are, which is 1.15 K2. That is, all these line currents are equal 1.15 Ki2, or that we are getting, if the load is balanced at the output side, the load currents at the input side, line currents on this side, all are equal 1.15 times Ki2, and they are, of course, if you see that they are 120 degree apart, or balanced three-phase line current is there. This is corresponding to a zero power factor at the load side. The same can be extended for if it is having a power factor, say 0.8, phase angle equal to 5 point or some phase angle 5 degree here. We can see that when this is the I2, this current is lagging this voltage by 5. Similarly, this current through the main is lagging the voltage by 5. Or in that case also, the same approach can be done, and we can see that one, the current through the the main winding through this, not main, through the line B and C, that can be obtained by vectorially adding the half of the teaser current to the current due to this load that is added, vectorially added, and this will be the resultant vector, which is the line current in the phase B and C. We can say that one. Or from watching this one, we can say that one, the line currents are, they are equal magnitude, and again they are shifted, or they are displaced by 120 degree. Or we can see that one, even when the load is balanced load with a power factor, with a lagging power factor 5, the output, the input side currents all are having the equal magnitude, and they are 120 degree apart, or meaning that the input is balanced, provided the load is being balanced. The two-phase load is balanced, the input side we are getting a balanced load current, meaning that load current magnitudes are same, and they are displaced by 120 degree. For this is corresponding with phasor diagram corresponding to a power factor angle 5, and this is corresponding to a unity power factor. In both cases, the input side is balanced. Now let us see a few observations of the Scott connection. One is that teaser transformer, that is the teaser transformer. Teaser transformer has root 3 by 2, or 0.86 times the turns ratio of the primary winding. Root 3 times, that is 0.86 terms of primary, or volts per turn is same, but voltage per turn is same, but this has got this much number of turns compared, of this main winding. The secondaries have equal number of turns. This N2, both are having the equal secondary turns, but the turns here is 0.866 times the turns of the primary, and this is the middle point. So the main transformation ratio equal to N2 by N1, which is equal to K, and the teaser transformation ratio is given by N2 divided by root 3 by 2 N1, or 1.15, or 1.15 K is the transformation ratio of the teaser transformer, and K is the transformation ratio of the main transformer. Therefore, from a balanced three-phase input, we are getting a balance, two-phase output. Therefore, if the load is balanced on one side, it is balanced on the other side. Therefore, under balanced condition, the main transformer rating, of course, 15% greater than that of the teaser transformer. That's another observation of a Scott connection. Now let us see a problem of this Scott connection. Two transformers are connected for a Scott connection operating from a 440 volts. Therefore, the line voltage is equal to 440 volt. Three-phase supply at the input side, and the two-phase furnaces are 200 volt of two phases. That is, here the voltage is equal to 200 volts, and this is if the total output of this furnace is equal to 150 kVA. Calculate the secondary to primary turns ratio of the winding of the each transformer, and also the line currents. What is the turns ratio of the teaser transformer and the main transformer, and also the line currents. Now coming to the main transformer, this is the main transformer primary and the main transformer secondary, and that primary voltage is equal to 440, that's the line voltage, and the secondary voltage, of course, we can see that one secondary voltage is equal to 200 volts. secondary voltage here equal to 200 volts. So the transformation ratio is given by N2 by N1, which is equal to 200 divided by 440, which is equal to 1 by 2.2. That is a K equal to 1 by 2.2 for this main transformers. And for the secondary current is equal to the load is given as 150 kVA. Total load is 150 kVA. For this is equal to 75 kVA and this is equal to 75 kVA. For the 150 divided by 2, that is 150 into 10 raised to 3 divided by 2 into the voltage equal to 200. Therefore, the corresponding current through this one at the secondary of the main transformer equal to 375 amperes. Same as this one also, 375 amperes this current. For this is the current through the secondary of the main transformer, and the primary winding current, because of this one, a voltage will induce that drives a current through this main primary, and that current can be calculated by this one into N2 by N1, or N2 by N1 already calculated as 1 by 2.2, or 1 by 2.2 into 375. 170.45 is the current through this main winding because of this load current. Now continuing the same problems, and here as we have seen the main transformer. Now we will see the teaser transformer. Teaser transformer, again the current through the secondary is already same as we have already seen, which is equal to primary voltage. Let us see the primary voltage is given by 440 volt is the line voltage. Therefore, the voltage across this one R and C, or this point, is equal to 440 divided by or into root 3 by 2, or it is equal to 381 volt is the voltage at the primary of the teaser transformer. And here the voltage equal to 200. Therefore, the turns ratio is given by 200 divided by 381 is equal to 1 by 1.905 is the turns ratio of the teaser transformer. And that is also equal to, we can say that it is equal to 1.15 K times, or equal to same as that one. Therefore, the secondary current, as we have already seen, the same as this one, which is equal to 375 amperes is the secondary current. 150 into 10 raised to 3 divided by, that is divided into 2 into 200. Therefore, that is the 375 ampere is the current through the teaser secondary. Now, the primary current is reflected on this side because of the transformer, the action here. What is the current reflected at this point at the primary side, which is equal to N2 divided by 0.866 N1 into whatever this current, which is equal to, we can get 197 ampere is the current on this side. Therefore, that is same as the line current, because the current through the teaser is same as the line current. Of course, now to calculate these line currents, half of this line current is vectorially added with the whatever the current we already calculated the main transformer current. That is this is added vectorial. The half of this current through this teaser, that is 0.58 of that one, that is added with this one, and this is the line current through these two phases, Y and B, same as this one. And just to calculate that one, line current through the primary winding or main winding through this one, the line current through this one is equal to square root of half of this primary current, or half of this teaser primary current, or 197 divided by 2 whole square, plus what is the main current, that is voltage, also the current that is because of the load current at the secondary side. What is the current? Already we calculated as it is equal to 170.45 whole square, or you'll be getting it is equal to 197 ampere, same as the teaser transformer current, which is all that is same as this one, 197 C. Or the line currents are all equal. That means that all are balanced at the input side, with the current equal to 197 amperes. Now let us see another problem. Two single phase furnaces working at 100 voltage are connected to a 3300 volts 3-phase main through a Scott connected transformers. Calculate the current in each line of the 3-phase mains when the power taken by each furnace is 400 kilowatt. Two furnaces, the voltages are, it is equal to 100 volt, here 100 volt, and the power equal to 400 kilowatt, and the power factor is given as 0.8 lagging. Of this power factor of this one equal to 0.8 lagging. This power factor equal to 0.8 lagging at this side. Now the question is that, neglect the losses in the transformer. You have to calculate the current in each line of the, what is the line current here? We have to calculate what is the line current of this at the input side. Now again we coming to the teaser. Let us see first the teaser transformer. Secondary, as you know, that the load is equal to, which is equal to, the load equal to 400 kW. And of course, the voltage is equal to 100 volts. Then you can calculate power factor is given as 0.8. then we can calculate what is the current through the secondary of the teaser transformer. 400 into 10 raised to 3 divided by 100 into 0.8, which is equal to 5000 ampere is the current through this one. And that is reflected here. How much is the reflected? You have to see that due to this current that is reflected in the primary of the teaser transformer, how much it will be, you have to calculate. For that one, we have to calculate, which is equal to N2 by this turns ratio is equal to 0.86 N1 into whatever this current, which is equal to, we'll be getting 175 amperes is the current through this teaser transformer primary, same as the line current IA. Therefore, the primary voltage is equal to 3300. Primary voltage here, line voltage, or the primary voltage of the teaser transformer is given by, of course, root 3 times, because 0.866 times, that is equal to 2858. This is the voltage at the primary side of the teaser transformer, and secondary side voltage equal to 100 voltage. And we have calculated what is the primary current we have calculated, which is equal to 175 amperes. That is current through the primary of this teaser transformer equal to 175 amperes. That is same as the line current IA. Now same thing we can calculate what is the current through these phases in C as well as B phase and C phase. Therefore, this is the phasor diagram corresponding to 0.8 power factor load. This is the secondary voltage and current. This is the teaser voltage, and this is the current to the, and this is the main voltage, and this is the current through the main winding load as such. Therefore, this is the phasor diagram corresponding to secondary, and that is because of that is reflected at the here, and that is added. This is the vector, that is the vector corresponding to the current due to the main secondary voltage. To that one, half of the teaser current is added, vectorially added, and then you'll be getting what is the line current, the phases B and C. Of course, as I already explained in the previous slide. Now continuing the same problem here, we can see that one, the main transformer, if you consider the main transformer, as we have already seen, the main transformer phasor voltage is equal, primary voltage of the main transformer is given by, of course, that is equal to line voltage 3300 volts, and secondary voltage equal to 100. Therefore, the ratio is given by 3000, the ratio N2 by N1, output voltage equal to 100 divided by 3300, or 1 by 33 is the transformation ratio of the main transformer. Now the secondary current already we have calculated, same as this secondary current, and which is equal to 5000 amperes. That is 400 into 10 raised to 3 divided by 100 into 0.8, or 5000 ampere is the current through the secondary main. That due to that one, that is reflected in this side. Now to calculate that one, which is equal to whatever this current, that is into this ratio 1 by 33, or 151.5 ampere is the current through the main winding because of this load current. But the current through the line is, you have to add this current with the half of the teaser current. Vectorially we have to add. Therefore, that is why that this vector, this is add, half of that one is vectorially added in order to get the total current, same as this one, this vector. Or this phasor diagram shows the how the current is being added, that the current in the main winding due to this load, to that one we'll be adding half of the teaser current. Therefore, that vectorial sum, this is the total line current in the phase B and C. So that we can see that when all the line currents are balanced, equal magnitude, and they are 120 degree apart. Therefore, now to calculate that, same as square root of 175 by 2, that is teaser current is 175 amperes, that divided by 2, that is this vector, square root of that square plus this vector, which is equal to, because of this one, what is reflected, that one, that is equal to 151.5 whole square, that is factorial sum of this one, that is this one, which is equal to 175 ampere, which is already same as this teaser current, because IA and the phase current IA, IB, IC, all we will be getting a 175 ampere. Means that if the load is balanced at this side, the secondary of this one, two phase, the input side, all the load currents are equal and they are 120 degree apart, or we are getting a balanced three phase input which is equal to 175 amperes. Therefore, the line currents are equal and they are balanced and they are 120 degree apart. Therefore, this is the phasor diagram corresponding to a load at the secondary side having a power factor 0.8. Therefore, this is the secondary phasor diagram and this is the primary side phasor diagram. Therefore, these are the line currents vector. They are 120 degree apart and having the equal magnitude.